techniques get more into a numerical approach. So what's nice about potential games, you could do a lot of analytical techniques, which we'll do. Okay, so let me get to the next slide. Here we go. So some preliminary potential games were discovered by Monderer and Shapley. So Dev Monderer, Lloyd Shapley, famous Lloyd Shapley from game theory. They've been shown to be isomorphic to congestion games. Computer scientists also use these to model internet congestion and network analysis. Of course, use rational potential game theory. You could read that in Wolpert and others. Wolpert was actually at the Santa Fe Institute. An analysis of certain boundedly rational potential games, statistical mechanics. And I mentioned that about Anderson, Gorey, Holt in 2004. This is a discovery I made. It was when I removed their mean field theory type of assumption from the quantum response. Statistical mechanics has been deemed a viable model to address some important questions in economics. And you could look at works of Brock and Durlaf. Wrote a very famous paper on this back in, I think it was like end of the 90s. And it yields things such as emergence and scaling, and we'll show that here. So let's look at the game theory. Consider a finite number of agents, and these are fictitious decision makers. So these could be people, they could be firms, they could be computers, right, with algorithmic trading and things like that. But ultimately, it's somebody or something who can buy or sell a good. We'll look at that. That's an example. We can, but don't need to imagine that each agent is located on a two-dimensional grid that we see over here. And the proximity doesn't have to be spatial. It could be, example, agents who bid on the same contract would be closest together. So that could be a company in LA and a company in Florida that are bidding on the same contract. They have more economic influence on each other than possibly two neighboring agents who have completely different biddings. So agents will label with the index I in some G, which is a set of agents. So at any moment in time, agent I can select an action or strategy, which we'll call XI, from a set A of strategy decisions. So for example, if A were the set -1, 1, -1 could represent buying and +1 selling. Also, A could be an interval of real numbers, representing the number of goods produced by a group of companies. And you could have a low number and a high number. XI is agent I's decision variable. So if XI were -1, that means agent I is buying. Now we'll talk about a configuration of the system. Well, that's just the set of all decisions, right? Or an ordered pair of all decisions at that moment. And so, for example, if we have the set of all -1s at the second to the last line, that would be everybody is buying. If we look at the last line, we have some +1s and -1s, which means some agents are buying and some are selling. We'll call the set of all possible configurations omega, which is the product of the A, which is called the pure state space. So that's just a space of all decisions that could be made. And then we'll give each agent will have a payoff function, which we'll call pi I. And notice each payoff is a function of all the other agents' decisions. And it gives the payoff agent I gets for a given state of the system. So for example, at the bottom, we see pi 4 with all ones for decisions gives agent 4's payoff if everybody is selling in that last example I did. Now, here's where we start to get into humanomics. Each agent will have an action function, AI, which is also a function of all the configuration or the decision variables. And it allows agents to control their behavior. So they can enact rewards and punishments towards other agents using this function. And just like the payoff, if we had A7 of all -1s, that would be agent 7's action if everybody is buying. Remember, -1 represent the buying state for it. This would be agent 1 is buying in the first position, The second position shows agent 2 is buying, and so on. Now, as I mentioned, we're only going to consider potential games. Now, what is that? It means we have a function v, again, of all the decisions, such that every agent's action function, AI, satisfies the following. Well, the derivative of their action function with respect to their decision variable, notice the A has an I and the X has an I, so it's the same agent, that is equal to the derivative of this potential function with respect to agent I's decision. So the potential gives is a sort of an aggregation of all the differences of agents' payoff. It's a global function that you could get agents' changes in their decisions from. So for those of you, this derivative, right, is a change in the decision AI with respect to decision XI. And let's see here. So the dynamics for the game, therefore, using this idea, we can. Yes.
Can I ask a simple clarifying question on the previous slide? Because so the v function doesn't have a sub-index I, right?
No. So it's a global function.
And so does it have more arguments than the AIs, or why does that hold, or is that a condition? I'm sorry if I'm very ignorant. It's a very basic question. But
that's okay. Yeah, it's the same arguments. So it's all the decision variables for each agent.
Okay, and the partial derivatives are only with respect to the own decisions. So like
yes. So yeah, it only right. So for each I, so if I had 1, it would be dA1 dx1 equals dV dx1. For 2, it'd be dA2. So now we're talking agent 2, a different action function 2, with respect to dx2 would be dV dx2, and so on.
Okay, I see. Thank you. Yeah.
So yeah, you can recover the derivatives. And what's this was in this paper by Shapley, right? And he shows the now this is not all games satisfy this, obviously, right? But Shapley showed these are and Mondera showed these are isomorphic to congestion games. But it's pretty robust. There's a lot of research going on potential games. And they're used in computer science and quite a variety of things. So let's look at the dynamics. Why do we want to look at those derivatives? Well, think of this. Agents are going to follow the maximum action direction. So if the action were just the payoff, what is this saying? DXI on the left in this red square, that tells you how is agent I going to change their decision? Well, what they're going to do, they would look at their action or say their payoff, and they would move it in the direction that it's increasing, right? If you look at the derivative, if the derivative's increasing, they're going to adjust their payoff in that direction. Why? Because they'll get more payoff. If it's decreasing, the derivative will be negative. They're going to decrease their decision because, again, their payoff will increase, right? So this is a myopic dynamics. They're only looking locally, right? Derivatives, when you're looking here, dx indicates you're only looking locally. You're making a small change in direction. So this would be a myopic model. And we'll assume that's reasonable because in a decision space, usually agents don't have a lot of information about decision space. If you think in all the restaurants in the United States, a restaurant in Los Angeles does not know what a restaurant in New York, in Wisconsin, in Florida are doing, right? So usually they only have partial information. So it's reasonable to assume they're going to make decisions that are myopic, that are going to be small changes from what's going on at that moment in time. Now we can put all this together with a potential. Up in blue at the top, we can replace dAI dxi with dV dxi. So then what we get are these dx's are equal to dV dx times dt. And so in other words, the change in decisions follows the gradient, what's called the gradient of the potential. Now, if we look at this to the right, imagine this square on the bottom is decision space, and up above is the potential. Well, you can see which way they're going to want to move. If the change in potential equals a change in payoff, well, it's going to increase if you move towards the center of this square, right, from any direction. So agents will move, and you can see the little arrows on there. Agents will move towards the center because their payoff will keep going up if they do that. Now, when they hit the top, the derivative will be zero. They'll stop moving, right? They'll have reached a maximum. And so the agents are moving myopically in that direction. So this is rational dynamics, and this is studied quite a bit out there in economics, actually. So what we're going to do is apply bounded rationality. And why? Because agents don't always have exact information due to random error. Bounded rationality, the errors are due to failures to choose most optimal payoffs and are intrinsic to agents. We'll actually show that I should change this. It could be extrinsic to agents too, as we discovered in this with the work with Vernon. Examples are experimentation. Sometimes people will experiment, right? They may think, oh, I should do this, make this decision, but I want to try something different and see what happens. Well, why is that? They have lack of complete information. So they don't know what will happen if they make a different decision. Unlike classical economics, it assumes agents do know what will happen. Sometimes they want to maintain the reputation of a product, so they won't sell it at a lower price. They'd rather lose money. And I know this, I'm a wine judge, and some wineries will do this, right? They will not sell for a lower price. They'd rather dump some of the wine and not sell at all than lower their price. In the fashion industry, some will do this too. It's called fast fashion. There's literally an article, I think in the New York Times, about one company burning their excess clothing because they did not want it to sell for a lower price. So they're clearly taking a loss. That is not, quote, rational, quote, behavior. Although Vernon would argue the opposite, because he had told me once, well, they have a reputation to maintain. But in the sense of classical economics, to lose money like that, if you're just following a profit function, that is not rational. Mistakes in judgment, right? Sometimes people just make mistakes in their judgment. Maybe if you've read Kahneman's book on thinking fast and slow, right? People use their system one, which is more based on intuition and heuristics. And so they won't use rational thinking. They'll just use heuristics or instinct to make a decision. So those are some motivations. So how are we going to model this? Well, we'll use what's called a Wiener process, which I won't get into the technical details here, but I'll show you a picture of it. It's basically a random process, right? So at every moment in time, it's going to be continuous. So you make continuous jumps up and down at random times. And we can see here, the horizontal line here is 0, right? So the random component will be positive all the way up to about time 4.5. Around 4.5, it goes negative, and then about 4 3/4, it goes back up positive. And what we're going to do is add this randomness to the decisions. So here's the stochastic dynamical model. Well, notice these first two terms, the dx and the triangle v, the gradient of v, dt. This is what we had before with rational myopic dynamics. Now we're going to add dw, which is that random component, right? The randomness. And we'll put a parameter in front of it called nu, which is a fluctuation variable that allows us to adjust how much influence the random part has. If we put nu equal to 0, this would be a rational model, right? Because it would zero out the random term. If nu gets large towards infinity, very large, well, then the random part dominates and agents are just behaving randomly without any rationality, right? They're making random decisions. This last part is just a boundary term. It keeps everything within a certain range of decisions. For example, if you're a company producing goods, you can't produce negative goods, a negative number of goods. So this last term will keep the process, say, from 0 up to some maximum number. You can make it so it won't go above a maximum number as well. So if you're talking like a percentage output, it would be between 0 and 1. This last term will keep it between 0 and 1. Because the random part might add a lot to it, right? Too much. Well, this last term will fix that. And this has a stationary state, this dynamical model. But before I talk about that, I'm going to talk about that since there's randomness here, we get a probability density function on decision space. So now before we could say all agents were buying or all agents were selling. Well, now we don't have that because we have randomness. So there's a probability now that all agents are buying, but there's also a probability all agents are selling. And we can't say they're doing one or the other for sure because of this randomness. So at any moment in time, they are doing one, but that moves around with some randomness. And if we track that, we get a probability density function. So if it were 50-50, there would be a 50% chance everyone's buying and a 50% chance everyone's selling if we restricted to those two states, for example. So f of xt gives the probability that agents make decisions represented by x at time t. F changes over time, but will reach a fixed function in the long run called an equilibrium measure. And why does it reach this? You could read the paper by, actually you could read it, I think I cited on the next one, Kang and Ramanan proved this in 2014, and which is funny because I was using this result back in 2005, right? This was actually shown, a looser version of this was proved in Anderson-Gorey-Holt's paper, but with free boundary conditions. And I started trying to prove this for when you had boundary conditions and you wanted to restrict decisions, like I mentioned before. And that was tough. So I was starting to learn about stochastic processes. And I kind of shelved that for a while, luckily, because this is like a 50-page paper that they proved this thing in. So I didn't have to do all that work, thank goodness. So let's talk about what they showed. Well, here, the evolution of that density function follows this differential equation called a Fokker-Planck equation, a partial differential equation. And when it's zero, you have a stationary state because why the decisions, your density is no longer changing in time. And so you get a stationary density. Now, it will reach us in the long run. Again, this was shown way back even in Anderson-Gorey-Holt's paper, because there's a Lyapunov function for this, which is the free energy from physics, right? So it's, or you could say constrained maximum entropy. So the Gibbs state is the stationary state. And again, proved rigorously in Kang and Ramanan's paper. Now, this is very interesting because this looks just like statistical mechanics. What we see on the left is 2 over nu squared. Now, remember, nu was that parameter in front of the random part. When nu was 0, it was zeroed out. The random part was perfectly rational. V is the potential. While in statistical mechanics, we have 1 over kt times E of x, where E is the energy and a negative sign. So we see a relationship, temperature is proportional to nu squared. So this is actually a fluctuation dissipation theorem in physics. And the energy is equal to the negative of the potential. So the analogy of a boundedly rational potential game to statistical mechanics is, as mentioned, nu squared is proportional to temperature, and the potential is a negative of the energy. Now, if you think about this, the more randomness, remember, as nu gets higher, nu squared will also get higher. Well, then T gets higher. So higher randomness means higher temperature or higher noise in decisions, right? The higher that nu squared was, the more randomness affects decisions. Decisions are noisier. The lower the temperature, the lower the noise in decisions. So temperature is a measure of the noisiness of decisions. When you have no noise, that's perfect rationality. So now let's take all this machinery and apply it to humanomics. What we need for humanomics is something extra. We need a gratitude configuration. And gamma ij will represent the gratitude or resentment agent I has for agent J. And so we'll visualize this as a bond between sites I and J. Remember, we kind of put agents I and J at 2 different points on a graph. Well, we can draw a line between them, and that line, depending on the value that line carries, will represent whether those agents have mutual gratitude or mutual resentment, or if they're just operating in a self-interested way. And so the value for mutual gratitude will give it a 1, for mutual resentment will give it a -1, and for self-interested behavior we'll give it a 0. Now, more generally, we could assume it doesn't have to be mutual. We could assume that agent 1 has gratitude for agent 2, but agent 2 resents agent 1. So that would be a non-homogeneous gratitude state. We're not going to consider that because to get a potential, it has to be mutual. And if you read Humanomics, that's not too much of a giant assumption, because often a more stable state is that there's mutual gratitude or mutual resentment. You typically get reciprocation, right, in general. Of course, that could be an interesting thing to model when it's not. And again, you would not have a potential. You'd have to use quantal response type measures to study that. But we'll keep it mutual for now, since that's a reasonable assumption and it makes the analysis easier. Now, we're also going to have 2 timescales, one for economic equilibrium, which is where we get the stationary state we mentioned before. And then we have another timescale for feelings of gratitude and resentment. So for example, if you have fast, high frequency traders that make decisions at microsecond time, well, your gratitude or resent for somebody is not going to change much, is not going to really change during that short period of time. Gratitude and resent might change more on maybe a daily basis or an hourly basis. You can model it to be longer, but it would certainly be, it wouldn't be changing in microseconds. I mean, you would probably be crazy if your attitudes were changing that quickly, right? You would be a very unstable person. So that doesn't really happen. So again, we have strategy variables, as we mentioned before. We have a payoff function, as we mentioned before, and we have action functions, as we mentioned before. I'll mention the action allows agents to reward and punish other agents when prompted by gratitude and resentment, and it can also reflect self-interested behavior. And I'll explain why. We're going to restrict ourselves to quadratic payoffs. Here's some formulas that are examples of quadratic. By quadratic, notice I mean x is multiplied. Remember, quadratic equations are second degree in x. Well, the degree of these, both of these equations are degree 2. This lower one's a little different. It's a quantity price type payoff, and you see these in Cournot models and speculator hedger models, where an x can be factored out, xk can be factored out. Let's talk about the action function now. So we're going to take those quadratic payoffs. Now, an action function is going to be a sum, and we're going to take the payoff of the other agents weighted by the gratitude configuration gamma ij out in front of the payoff. Let's look at some examples of this. Now, if AI were pi I, well, that means all the other gammas are 0. We'll assume gamma II is always 1. In other words, an agent always has gratitude for themselves. They're not going to act against their own interests. So if all the gammas were 0, we have self-interested behavior. Agent I's action is to maximize only their own payoff, and they don't really care about other agents. Now, if gamma I were not 0, if the gamma ij's were not 0, if say they were plus or minus 1, if they were plus 1, let's say we had 2 agents, so agent I and agent J, well then action I, agent I's action would be their payoff plus agent J's payoff. If they, and we'll show why, if you add, that will actually improve the other agent's payoff. Now that requires certain correlations to hold, which we'll look at in a moment. Now, if gamma is -1, now notice agent I will have their payoff minus agent J's payoff. So they're trying to maximize their payoff minus agent J. So it's having a minimizing effect on agent J's payoff. So they're punishing agent J if there's a subtraction. And this is where we actually can recover this lost information I talked about at the very beginning. So this form is for aligning ferromagnetic interactions on the footnote below. It was shown in our paper for opposing interactions, or so-called anti-ferromagnetic in physics. The addition and subtraction of payoffs can be, in other words, adding payoffs can be punishing and subtracting payoffs can be rewarding, which is the reverse of what we're talking about here. So how you punish and reward depends on the structure of the game, which is what we showed in our paper. But we will assume agents learn this with repeated experimentation. They'll learn how they can control their action to result in reward or punishment towards other agents. And this is kind of in the spirit of even mean field game theory, where it uses a control theory approach where agents control their decisions. It's not quite at the level we're doing it here. We're doing it in a much more sort of general method, but you could look into that. That's an interesting approach. Let's look at a two-person aligning game. Now, why is this called aligning? Because this interaction J that we see in both of these payoffs is positive. If J were negative, it would be anti-aligning or opposing or anti-ferromagnetic in physics. Physicists would call this ferromagnetic system. And why is that? Because if you remember, well, we'll see the potential, and I'll explain that when we see the potential for this. Now, this is what we call interaction heterogeneous, because why? The H1 and H2 are different. Now, pi 1 is agent 1's payoff, pi 2 is agent 2's payoff. So notice the interaction between them is the same, but they're, these H's, the linear terms, are different, can be different. Our gratitude configuration is a single variable. Now we'll only consider -1 and +1. So agents will be interacting with each other. So therefore they will either have gratitude or resentment. Later we'll compare that to when they act in just self-interest. Now here's the potential, V, and you can verify the derivative of this with respect to x1 equals a derivative of payoff 1 with respect to x1, and the same for payoff 2. Now, why do we call this ferromagnetic or aligning? Because remember, the Gibbs measure is roughly e to the power v. That's the probability. And notice that's going to be higher when x1 and x2 are the same sign because J is positive. And that will be e to a positive number, which is larger than e to a negative number. So there's a higher probability when x1 and x2 are the same sign, right? Either both positive or both negative, their product will be positive, and therefore they will have a higher probability. So that's why it's called aligning. They have higher probabilities are given when they make the same decision. Now, we need gratitude to deal with this gratitude variable. We're going to assign a probability. We're going to say agents have mutual gratitude with probability P, and therefore there's going to be mutual resentment the rest of the time, which is 1 minus P. So if P were 1/2, they would have gratitude, mutual gratitude half the time, and mutual resentment the other half of the time. If P were 0.25, they would have mutual gratitude 1/4 of the time and mutual resentment 3/4 of the time. So P is the empirical frequency of mutual gratitude. So like before, we get the Gibbs measure. There's that e to the beta v. A partition function, we're going to use this. It's a generating function. It can be used to calculate mean payoffs and probability theory, right? The free potential is actually the generating function. If you take derivatives of this f function in blue, you will get mean values for different variables. And so let's take a look at that in a moment. But first, before we do that, we're going to talk about, we have this probability measure, so we can get the expectation of a function with respect to this probability measure. So let's say an agent's payoff. Well, remember, there's a probability agents can be in any state. So we want to take the average over all those states. So we're talking about average probabilities of payoff. So we need to take averages. And we will use that Gibbs measure to get averages. But we need to go a step further, because once we take the average with respect to the Gibbs measure, that's with respect to the X variables, as we can see on the far right in red. There's still this gamma variable. So since over economic decisions in equilibrium, remember we assume fast traders, gratitude stays constant. So gamma is a constant in the red equation. But over longer periods of time, that can change. So we're going to take another average over the probabilities with respect to the gamma variable, or gratitude and resentment. Remember we said if it were half and a half, there would be resent half the time and gratitude half the time. So we're going to take half and half of each of the states above, where they have gratitude and where they have resentment. So we need to average over that as well. So that is actually a quench mean. In statistical mechanics, this is exactly what you do with a spin glass model. So right away, we see when we make these assumptions, we get a spin glass model in statistical. So here we go. Remember I said we can use that generating function to calculate average payoffs. Well, the average payoff for player one up on the top in red, turns out we get this function here, and that's the hyperbolic cotangent in black. For agent two, we get this function here. Now, this is when gamma is -1, which is resentment. When it's not -1, it's much harder. Why? Because -1 zeroed out the quadratic terms. If we go back, see the potential, see how it's 1 plus gamma up above in red? Well, when gamma is -1, that's a big zero, and the quadratic part goes away, and it's easy to integrate the rest of this. When gamma is not 1, we get more complicated expressions. And we can see here, we just need to use these to compute payoff. So up on the top third, we have the expected value of x1, x2. In the middle, we have the expected value of x1. On the bottom, we have the expected value of x2. Well, that's all we need to compute the expected value of payoffs. So how do we do that? We see at the top, the average of pi 1 of player 1 will be by linearity. We get this function here. So, and for payoff of agent 2, again, we get the same thing. So you can see we only need those three expectations for x1, x2, x1, and x2. Well, now that we can get those, we want to take the average over the gamma variable, or the quenched payoffs, over gratitude and resentment. And we're going to put a bar above. So we're going to write that as pi 1 bar and pi 2 bar. And really all we need to do is weight the resentment by the probability of resentment, and the gratitude average with the probability of gratitude. And let's look at some numerical results. So that's basically how to set up the model. We'll take some specific results, j equal to 4, h1 1, and h2 6. Now I'll point out, since h1 is lower because of correlations, agent 1 will have lower payoff. h2 is higher, so it's 6, so agent 2 will have higher payoff in these type of aligning models. And gratitude will be a 1, and resent will be a -1, as we mentioned before. So here's the first graph, and this is very interesting. It's the average payoff we see on the left on the vertical axis, and on the horizontal axis we see beta. Now beta is 1 over the temperature. So since it's the reciprocal of temperature, remember we said higher temperature was more random, less rational. Well, that means higher beta is more rational. It's the opposite. Lower beta is more random. So here we're taking mutual gratitude and mutual resentment to be 50-50. And we see these payoffs at beta equals 0 down in the lower left corner at 0, 0. Behavior is purely random, and all payoffs are 0. Why? Because the x's become decorrelated, and their averages from -1 to 1 are 0. As beta goes to infinity, the payoffs approach the Nash equilibrium. Remember, beta approaches infinity, temperature approaches 0. And if you follow the gradient of the potential, you go to the maximum of the potential. And it was shown in, well, that's kind of well known in Shapley's paper. The maximum of the potential is a refined Nash equilibrium. But it turns out, and it's proven in our paper, you can see on the far right, these curves are converging. And in fact, at infinity, they all converge to the same thing. And let me explain these curves. The lower curve on top, the red one, is the punishment, mutual punishment payoff. The blue one up on top is the mutual gratitude payoff when agents are working together. So you can see there's higher payoff. The black one is their average, their 50-50 average. So this is what the black one you expect on average. So you can see when agents have gratitude for each other, they have higher payoff. When they resent each other, they work against each other, they punish each other, have lower payoff. Well, when it's perfectly rational, this doesn't work. The payoff for mutual gratitude and mutual resentment are the same, right? So changing your decisions is not going to matter in this particular model, whether you have gratitude or resentment. So we see corollary, the Nash equilibrium has no predictive value in this particular model. So we have to go to the Gibbs measure. We have to go to the left of infinity, and we see it's doing what it should in this region. When there's mutual gratitude, they work together, they reward each other, and they get higher payoffs. When they punish each other, they get lower payoffs. We also see there's a learning curve, right? These curves are concave, so there's decreasing marginal gains as knowledge increases. So this is very interesting. As beta increases, remember, as we go to the right, agents are getting more rational. How do they get more rational? Well, they put in work to get more information about the system. It takes effort. And we see the gains are really strong at the beginning. It goes almost straight up, but then it starts leveling off. So the more effort they put towards getting more information to be rational, more rational, the less the payoff is. So we see bounded rationality could actually be due to intrinsic properties of the game, namely diminishing rewards for higher rationality. So what are agents going to do? They're going to stop. They're going to stop being more rational. They're going to say, well, I've learned 60% of what's going on. That's enough. I don't need to learn more because it's not paying off. So that's an interesting result. So we see information is lost about this also in the Nash equilibrium, since all those curves converge. This was also outlined in a paper in the footnote at the bottom by Donald Sari and Dan Jesse in 2016, found information is lost when using Nash or quantal response. The lost information in quantal response is recovered here through rewards and punishment. Let's look at another curve. This is the quenched and self-interested payoffs versus temperature. So now we're going to go back to temperature. So now as we go to the right, this is more random behavior. As we go to the left on the graph, it's more rational behavior. And we can see they all converge at the top. And these are the averages, remember, over gratitude and resentment. So we see here for different levels of gratitude and resentment, the curves on top are for agent 1, the blue and the black, the curves on the bottom, green and red, are for agent 2. And we see these dotted curves, the blue ones are getting higher. Well, that's as P gets larger, right? They're getting higher. So as agents have the probability or the proportion of mutual gratitude gets higher, the payoffs go up. So down at the bottom, this dotted curve, this dotted blue curve, is when P is 0.2 or 1/5. So that means there's mutual gratitude 1/5 of the time and mutual resentment 4/5 of the time, or 80% of the time. So 80% of the time they're punishing each other and losing money. So you can see why the mean payoffs are the lowest. As we go to the top one, the solid blue curve, we see that's when P is 80%. So on the top one, agents reward each other 80% of the time. 80% of the time, there's mutual gratitude. Now, the black one is interesting. That's self-interested behavior. That's when the agents do not interact. And what we see is something very interesting. if there's too much punishment, it's better just not to interact with the other person, right? To not reward and punish and enter into any interaction with them. It's better just to be self-interested and maximize your own payoff. When the gratitude gets high enough, your payoffs can outweigh the self-interested case, as we see with the higher blue curve that's solid. And the same goes for agent one. Now let's look at this. There's going to be a critical value where this happens. Let's average over temperatures. So let's take an average of the payoffs across all temperatures. Say we don't know how rational it will be at any given time. Let's make an assumption that, agents are between 0 and 15 temperature uniformly. In other words, the same probability. It's like rolling a die. Same probability they'll be at any one of those degrees of rationality. So we're going to take an average of these payoffs, the payoffs where they interact and the payoffs where they're self-interested over the different temperatures. And what we see here is we get this curve here. Now the black line again on top is the self-interested payoff over the average of these temperatures for agent one. Notice agent one has higher, or agent two, I'm sorry, the top is agent two. Agent two has higher payoff than agent one. And notice that this tilted curve, right, the slope curve is the quench payoff when they interact. Now, there's a point here where these intersect. So what's going on there? When they intersect, they're making the same amount of money when they act in their own self-interest and don't interact as when they do interact. Now, when you go to the right, you see the blue curves above the black curve. It pays to interact. So we see there's a critical P on the bottom, the horizontal axis is P. And notice that probability here where these curves intersect at the top is about 0.553. Well, that means there has to be mutual gratitude 55% of the time for agents to want to interact with each other. If it's below that, they make less payoff. They're not going to interact with each other. They're just going to act separately in their own self-interest. So we see there's risk aversion here, right? So it's not P equals 0.5 where this happens. If it were 0.5, they would be indifferent to the amount of gratitude and punishment. So we see agents will not engage with each other until there's more than 50% of mutual gratitude. So they have an aversion to resent. Now notice agent one at the bottom, it's even farther. The intersection's farther to the right at 0.597 or about 0.6. We can see it's above about 0.6. So agent one with lower payoff is even more averse to resentment. Agent one will not engage with agent two till there's about 60% mutual gratitude. So this is sort of consistent with axiom 4 in humanomics, that agents are averse to resentment. And also shows that there's agents with more money are willing to take more risk, right? They will jump in. If there's more resentment, they're willing to risk it. Well, it makes sense because they have more money. It's not going to affect them as much. Well, this is not built into the model. It's just a property of this model. What's interesting, if you take very high temperature, they are not risk averse. Remember, they start getting more random and non-rational. These intersections can happen over at like 0.3. So that means agents will engage each other when there's a lot of resentment, if they're non-rational enough. So this is a current area of study, is where does that cutoff occur at 0.5, at what temperature? So in the conclusion, what have we introduced? A simple tractable model that implemented fundamental elements of humanomics, where mutual gratitude and resentment with reward and punishment in the form of higher and lower payoff. We included bounded rationality and also timescales for economic equilibrium and feelings of gratitude and resentment. We see that this is a quenched model with faster economic equilibrium, which gives new insights into critical quench probabilities. In spin glass models, they don't read nearly as much into these probabilities they have much more meaning, say, in these models than they do in physics. They carry more information here. We see agents are resent averse, consistent with axiom 4. And we see the Nash equilibrium does not have any predictive power for this particular aligning model. So we have to use the Gibbs measure, right? Infinite agent homogeneous interaction model, if all the H's were the same, would be exactly a spin glass, but it's a little different than a spin glass in physics. The disorder comes from random high temperature behavior, not frustration. Frustration means the signs can get negative. In this model, we did not allow the signs to get negative of the interactions. But the result is for high temperature behavior, you get effectively higher temperature or more randomness, which creates disorder, which is different than the frustration of classical spin glasses in physics. What are some areas of future research? Create a model where the timescales of economic equilibrium and feelings of gratitude, resentment are the same, and these might interact. The variables of gratitude, resentment, and the economic variables would interact. A spin glass infinite agent homogeneous interaction model. To do more research on that, and my guess is it has a phase transition. What is that phase transition in this model? That would be interesting to study. What does it mean? In similar models, as I mentioned, we discovered flash crashes, right? So I wonder what that would be in this model. That would be worth looking into. The anti-aligning models, when J is less than 0, well, those are when agents want to do the opposite of what other agents do. Like in a Coronel model, if everybody's buying, you want to be a seller, right? You want to do the opposite of the majority. How about an aligning model like we did with 3, 4, 5, or 6 agents? Probably have to be done numerically. Do similar results hold as n equals 2 in this paper? Finally, to look at homogeneous gratitude configurations, where the gratitude and resentment need not be mutual, could be one-sided. That might be an aberrational case, but it might be interesting. And that ends the talk.
Mike, thank you very much. The floor is open for questions, so feel free to just unmute yourself and ask your question.
Hi, Michael. Thank you for the really interesting talk.
Yes, thank you, James.
Could you go back to the slide where you first showed the split between the mutual gratitude payoff and the mutual resentment payoff, and how when you go to beta equals infinity, there's no split anymore, and the Nash equilibrium doesn't predict any differences there?
Yes. So I think let's see here if I could find this here. Yeah, so I think that would be here. Oops. Let me try that again. Okay, so I think that would be
yeah, exactly.
Yeah,
thanks. So could you just help me understand? So the reason why the Nash equilibrium has no predictive value when beta goes to infinity is that I guess there's no noise in the system. There's no noise in agents' behavior, so they can't discover which strategies work better than others. Am I understanding that right?
Well, it's more, it's more a result of the structure of the payoffs, because they are what we call aligning or ferromagnetic in the physics talk, right? But they're aligning. They're quadratics. These quadratics do not have an internal maximum. They're actually going to be convex, right? They're not concave. So the maxima are going to happen at the edges, not in the interior. And it turns out just a property of this, these action functions, they, even if you reward or have payoff, the strategy at which you play, it does not change the payoff. So if you play that maximum strategy at perfect rationality, which is the Nash equilibrium, for the action functions, and you use that to go back and compute payoffs, the payoffs are the same when there's mutual gratitude or mutual resentment. So it's kind of more of a structure of the of what's going on with the action functions, right? And because of that, the fact that that maximum occurs at the edge, you kind of lose the effect of reward and punishment, right? It's almost like gaming the system. Really, you're finding a strategy where if an agent tries to subtract your payoff, you're not going to make any less, and if they add your payoff, you're not going to make any more. So maybe gaming the system is not a good word, because you don't win or lose with this. So it's and in fact, that's kind of an essence of a Nash equilibrium. You try to play something where no matter what the other agents do, your payoff won't change, right? So if you think of it that way, it kind of makes sense, right? So, but if you can find a strategy to play so that other agents are not able to affect how you behave, well, then they're not going to be able to reward and punish you in this sense. And furthermore, that assumes you know the complete state of the system, right? You know, if it presumes you know what everyone else is doing, and it also presumes you know how to play in that manner when you know what everyone else is doing. In a large scale game, right, that's not reasonable. Agents don't know what everybody else is doing. So there is noise just because there's so much information that's impossible for a person to track. For a two person, it's probably a lot more along those lines. I mean, it's the essence of the Nash equilibrium prevents you from being able for other agents to be able to help you out, right? Because does that make sense?
It helps, yeah.
Yeah.
Thanks.
Yeah. Great question. Now I've never thought of it that way before. That was an outstanding question. In fact, I'll have to use that in future talks. Any other questions?
I also don't see any raised hands. Mike, Vernon Smith did not, at least I didn't see him. I was monitoring the participants, so I did not see him. Maybe, yeah, I don't know if he has texted you or contacted you.
Yeah, I hope he didn't get the wrong time. So
yeah,
try to log in an hour or something right there. Yeah, okay, that's okay. I'll send. Yeah, Vernon was gonna try to make it, but it looks like he didn't make it. So, but that's okay. I think this is being taped, so he could also watch the video. I
will send this to you so you can share it with whoever else you want to share it with. Yeah, Mike, actually, maybe there are some more questions coming up, but maybe you can spend a couple of minutes towards the end to actually also tell us about your work on AI at Eureka. If that's something you feel like talking about, I would love to hear more.
Yeah, absolutely. I know some of my Eureka colleagues are here. Some of the stuff I've done with artificial intelligence, well, we built this system, what's called intelligent trades claim management. What it does is, I'll give the short run of this. If you have often you have a retailer and a manufacturer that interact, right? So the manufacturer will sell products to a retailer. So for example, say you have Tom's toothpaste and they sell toothpaste to Mother's Market. And they'll tell Mother's Market, well, if you sell 500 of our tubes of toothpaste this month, you'll get a 10% discount on them. So that's what the salespeople tell them, right? And that's called a promotion. And you see this, if you go to a grocery store, you'll see these little tags that say buy one, get second one 50% off. Or maybe it'll just be a amount off. This week only $1 off, you know, Tom's toothpaste. So what happens, the retailer will sell these, and what they do in America is they will only pay, you know, if they were told they get 10% off, they'll only pay 90% of their bill when they ordered the 1,000 tubes of toothpaste. So they'll pay 90% of their bill. So back to the manufacturer, Tom's toothpaste, the people in accounting say, how come they didn't pay 90% of their bill? Now you got to remember, in these big companies, there's not a lot of communication between different departments, right? Probably, like I would say, even at universities, right? Most people in biology have no idea what the people in sociology are doing, right? So it's kind of like that. And so what happens is the people in accounting will get this bill that wasn't totally paid, and they'll try to find out why. They're going to red flag it. It wasn't paid. They're going to go through promotions, and they might, when they get their promotions in their database, there can be upwards of 50,000 of these promotions. Now, if you're the person trying to match this, you are not going to want to go through 50,000 of these and try to find a match. Now, you can narrow it down using some basic filters, you know, search filters, but there's still a lot. You might get, maybe you might get it down to 100 or something like that, but even 20, but who wants to go through and look at all the details of these? Well, we came up with using some artificial intelligence, a way to reduce that to 3, and we could get the correct one or more within those 3 with about a 99.7% confidence. And so that uses, and we tested several models to do that, do that matching. And a neural network one originally, but when we put in some, when we increased the bias and on the decision tree, when we injected about 10% error into the training set, it actually outperformed the neural network. So we actually use a decision tree to do a lot of that claims matching. So that saves people hours of time. That's one example, right? We've done. We've also done some fuzzy matching algorithms. So say a retailer and a manufacturer have slightly different descriptions of a product. If you don't have the SKUs, sometimes you need to use those descriptions to match. Well, they don't exactly match. So you have to, so we actually I invented an algorithm to help with that. But we use some ideas from natural language processing. And actually this, I augmented it with an entropy. We're using entropy measure from information theory to match it. And so that's another example of some stuff we do that's related to natural language processing.
Sounds super exciting. So yeah, something with some of our colleagues at the Growth Lab are experimenting with, but for non-commercial purposes.
Oh, nice.
So
yeah.
Good to have you as a contact, and maybe at some later point down the road, contact to consult on issues.
Absolutely, I'd be honored. I'd love to. It'd be fantastic. Yeah, we're also experimenting with vision, computer vision. We have a plan to start a project with Chapman University to get students to work on this and to go out, take pictures of aisles and try to determine, this was my colleague's idea, Gustavo Iris de Castro, but to have, to detect when promotions are going on, right? We want to detect those and to use computer vision. So with their cameras, to train them to detect if this item has, or even if this aisle has a promotion, but specifically if we can hone in on this product in this aisle, like say Tom's toothpaste, you train it to sense when there's a promotion. Maybe the neural net, it's a vision problem, will recognize a red tag or a tag that's a different color or a different shape. So that's something we're also interested in. So that gets into computer vision. So that's something we're going to explore. Oh, another project is experimental economics, believe it or not, with our user interfaces. And there was research done. I saw this, it was at Chapman's Economic Sciences Institute, but there's a guy from Spain, I'm having trouble remembering his name, but he did studies on how you present information to people and how they search that information can have different results on their accuracy. And so if you're trying, say often you're presented products, its attributes are listed horizontally. Like say you want to buy phones. So vertically, they'll list the different phones, iPhone, Samsung, LG, and across the table, they'll list memory, pixels, apps, number of apps you can obtain, they'll list all the attributes. And he showed, depending on how you search this, if you search across or if you search down, you'll make better or worse decisions. And so his studies, of course, were ultimately payoffs, right? He did experiments using payoff, but he showed that you should encourage people to search by product first, and because that's when they make the best decisions and make the most accurate decisions. So that's important, because if we use a better interface, people will use our software better, and it'll look like our software performs better, right? Is better. And this is really interesting because we're getting more performance purely by influencing the user. It's purely behavioral economics, right? By influencing a user to get better results. So there's another commercial application of experimental economics.
Really cool stuff, both cool work and great research. Well, if there are no more questions, I'd like to thank Mike for excellent presentation, and please stay in touch, and thank you.
Absolutely, it's my pleasure, and thank you all.
Thank you.
Okay, bye.
Thank you.